Hello, and welcome to the presentation of North American spike fatigue failures, the effect of fastener stiffness. My name is Khachaturian, and I'm a second-year master's student and graduate research assistant at the University of Illinois at Urbana-Champaign. I'd like to begin today's presentation by acknowledging our project sponsors and industry partners. Without their time, expertise, and dedication, none of this work would be possible. First, I'd like to provide a brief outline on today's presentation to explain where we're going. I'll start with a background to explain the problem as to why we're studying fastener stiffness. Then I'll break the project down into project thrust areas, and this will lead us into the motivation and overview, where I'll present today's driving questions. Then I'll provide a brief naming convention so that we're all on the same page, and then we'll get into the specific lab work conducted as well as the results, and I'll finish today's presentation with some brief conclusions. Before we get into the fastener stiffness analysis, it's important that we have an understanding of the extent of spike fatigue failures. Fatigue failures are identified on 7 separate railroads and have been the cause of 11 major derailments identified on 4 separate railroads. Now, inspection of these fatigue failed spikes are complicated enough because they require manual walking inspections and tapping of each spike. This is because these fatigue failed spikes fail at approximately 1.5 inches below the top of crosstie. This means that with your naked eye, you're not going to be able to identify a broken spike. And the common location of failures are high degree curves in special track work, higher tractive effort or braking force, and we found no correlation between specific spike hole locations and failed spikes. We found broken spikes in all 4 relevant spike hole locations. And then finally, we've most commonly seen these fatigue failed spikes in new or very good condition ties. Additionally, we've determined that spike fatigue failures occur primarily in elastic fastening systems on curves. And this is a result of 3 primary contributing factors related to load transfer. The first is an increased longitudinal load. With the presence of elastic fasteners, load is now being transferred directly into the spike as opposed to anchors transferring through the crosstie. The second is a reduced friction between the plate and tie. Due to the wave action of the rail, there's uplift between the plate and tie before and after the wheel of a train pass. This results in the friction component being eliminated from the load path, thus significantly increasing load transfer through the spikes. Finally is the third bullet point, which is an increased rail seat load. Now I'll note that this bullet point we're going to be directly addressing in today's presentation, and results that we can expect is that elastic fasteners are stiffer, thus resulting in distributing loads over fewer ties, which results in an increased rail seat load. Historically, there have been several mitigation approaches that have been implemented in the field in an attempt to mitigate spike fatigue failures. And these mitigation approaches within fastening systems are summarized here on slide 6, which includes increased spike steel strength, addition of rail anchors, changing cut spikes for screw spikes, plate cleats, and finally screw spikes and spring washers. Now, to summarize all of these mitigation approaches, each one of these approaches largely just resulted in fatigue failure being delayed, but not necessarily prevented. So now that we have an understanding of both the background and the extent of spike fatigue failures, as well as the previously pursued mitigation methods, how does today's presentation on fastener stiffness relate to that problem? Well, today we're going to investigate if additional spike failure mitigation methods can be found from the quantification of the effect of fastening system stiffness and the effect of plate clamping force or uplift. And we've broken this entire project down into 3 separate entities: laboratory work, analytical modeling work, and field work. However, we do not see these 3 as mutually exclusive, instead as 3 parts of a puzzle working in cohesion to provide one comprehensive mitigation approach to industry partners. And today we're primarily going to be focusing on laboratory work conducted. The motivation for the fastener stiffness analysis that we're going to be discussing today is best summarized by the driving questions and hypotheses as presented on slide 9. The first driving question we are going to aim to answer today is how are fastener stiffness and rail seat load transfer affected by fastening system characteristics? Second is, how does fastener stiffness affect track stiffness? And finally, how is load transfer affected by plate clamping force or uplift? And the three hypotheses that we're going to be challenging today is different fastening system components will result in varying fastener stiffness, increased fastener stiffness will increase spike load, and finally, plate clamping force will decrease spike loads. And we're going to start by first focusing on these first two driving questions and hypotheses. By conducting a preliminary analysis on the effect of fastener stiffness, we can challenge the hypothesis that increased fastener stiffness will increase spike load. We will do this by using this equation pictured here on slide 11. Now you can see that Ka, which is longitudinal track stiffness, is a function of both Kp and Kb, which is fastener stiffness and ballast stiffness. Now in order to understand the effect that fastener stiffness has on the overall longitudinal track stiffness, we will hold ballast stiffness constant at 40 kips per inch, and we will vary fastener stiffness from 0 to 400 kips per inch. And you can see the results here presented on slide 12 that initially, as fastener stiffness increases, track stiffness also increases. However, this effect that fastener stiffness has on track stiffness eventually tapers out past a certain magnitude. Thus, it can be concluded that track stiffness is more sensitive to the lower stiffness value within the track system. So now that we've qualitatively understood how fastener stiffness affects track stiffness, we now want to quantitatively understand the effects of fastener stiffness through the use of controlled laboratory experimentation that will be presented on the preceding slides. And before I get into specific laboratory work conducted, I first want to provide a brief naming convention so that we're all on the same page and have an understanding of which fastening system components I'm referring to for each setup. So pictured here on slide 13, all four of the setups that we used in the lab are comprised of a single rail seat, which is a timber block, and the anchor-only system has 4 cut spikes, a plate, and the anchor. E-clip only has 2 E-clips, 4 spikes, and a plate, and the anchor and E-clip includes both the 2 E-clips and anchor. And the tension clamp has 4 screw spikes and spring washers and 2 W12 clips. And we will use each of these 4 setups for 2 separate characterizations. The first is a longitudinal stiffness characterization, where we will achieve 5 replicates of each of the 4 setups: anchor only, anchor and E-clip, E-clip only, and tension clamp. Then once we've characterized longitudinal stiffness, we will then characterize spike load, where we will run 5 replicates of setups 1 through 3 again. So beginning with fastening system stiffness characterization, the purpose of these tests, or these experiments rather, are to quantify fastening system stiffness. And the instrumentation we're going to be used is pictured here on the right side of slide 15, where for displacement we will be using 5 potentiometers, which are 2 on the crosstie, 2 on the plate, and 1 on the rail. And then we will also be receiving displacement data from our actuator. And for force data, that is primarily going to be received and acquired from actuator load cell data. And for the test procedure, we will be using a modified longitudinal load restraint test from ARIMA Chapter 30, where we apply a longitudinal load until slip. All the while, we will be monitoring both displacement and load. And to provide some brief definitions, we're defining stiffness as the slope of the data between 500 and 2,500 pounds of longitudinal load. And slip we're defining as abrupt movement of the rail relative to the tie, leading to sudden drop in load. And so jumping into some results here on slide 16, this figure is made up of 4 representative curves for each fastening system setup, which again is anchor only, E-clip only, anchor and E-clip, and tension clamp. And the one thing I want to make sure we identify here on slide 16 is within this region used to calculate stiffness, which is again from 500 pounds to 2,500 pounds of longitudinal load, you can observe that the slope from each representative curve has some variance in it, meaning that there is some stiffness variance based on each fastening system setup. Thus, the results are summarized here on slide 17, and the one thing I want to make sure we identify is the fastening system stiffness variance that is introduced by the presence of these E-clips. Now, with these E-clip fasteners, significant stiffness variance is introduced when compared to anchors or tension clamps. However, stiffness magnitude of these elastic fasteners is approximately 2 to 3 times greater than the anchor-only system. And so the trade-off is, with the presence of these E-clip fasteners, significant stiffness variance is introduced. However, stiffness magnitude is significantly increased. So now that we've characterized how different fastening system components affects variance in fastener stiffness, we now want to translate this back to the overall bigger problem, which is how does this variance in fastener stiffness relate in variance in rail seat load? And we can do this by using an analytical model that simulates 3 locomotives with 10 kips per wheel of tractive effort and a ballast modulus of 2,000 pounds per inch. And you can see here right away, pictured here on slide 18, that same variance we see between on the effect of fastening system components and variance in fastener stiffness, that same variance is not seen as it pertains to rail seat load variation. You can see that the rail seat load variation dependent on fastening system components is significantly lower than the stiffness variance. However, I will note that with the presence of elastic fasteners, rail seat loads are increased, although minimal. They are increased by approximately 5% when compared to anchor-only fastening systems. Thus, it can be concluded that fastening system stiffness plays a minimal role in load transferred to the spike. So now that we've addressed these first 2 driving questions, we now want to address that third and final driving question and hypothesis, which is, how is load transfer affected by plate clamping force and uplift. Similarly to the preliminary analysis we conducted for fastener stiffness and its effect on track stiffness, we can conduct another preliminary analysis to determine the effect of clamping force on spike load. And using an analytical model with screw spikes and spring washers that apply a clamping force of 4,000 pounds and 13,600 pounds, and applying a longitudinal load of 2,500 pounds to the fastening system, we can determine that with the presence of a 4,000 pound clamping force, nearly 70% of spike stress was reduced. And comparatively, when you have 13,600 pounds of vertical clamping force, 80% of spike stress was reduced. And this is because when you have such significant plate clamping forces, most of the longitudinal load is then taken by friction as opposed to being transferred through the spikes. Thus, it can be concluded that vertical clamping force significantly reduces the spike load. Now that we've seen these results through the use of an analytical model, we now want to challenge or validate these results through the use of controlled laboratory experimentation. And so pictured here on slide 21, the purpose of this lab experimentation is to quantify the effect of vertical clamping force and use of anchor on spike load. And the instrumentation is similar to that of used when we were characterizing fastener stiffness, and it's using an applied force from actuator load, and then spike load is going to be analyzed through 4 instrumented spikes, and each of these instrumented spikes includes a single strain gauge per spike and 4 spikes per rail seat, as I previously discussed. And the test procedure we're going to be following is we're going to vary the presence of plate clamping force, where we have 0, 5, or 10 kips of downward plate clamping force, or we're also going to apply uplift until a visual gap is seen between the plate and cross-tie interface. And then we are going to be applying a longitudinal load from 0 to 2,500 pounds while monitoring load applied, and spike load. In results here pictured on slide 22, when you have a 2-kip longitudinal load and 0 vertical clamping force, you can see that when E-clip is not present, spike load is 0. So with the anchor-only fastening system, as we previously discussed and hypothesized, 0 load is being transferred through the spikes. However, when you have the presence of an E-clip within the anchor and E-clip or the E-clip only fastening system, a large load distribution is being transferred through the spike. Upwards of 92% of load are transferred through the spike with E-clip only fastening systems. And now analyzing the effects of various vertical clamping forces when you have that same 2 kips of longitudinal load, and analyzing just the E-clip only fastening system, we can see similar results that were output by our analytical model. With the presence of 5,000 pounds of downward clamping force, nearly 70% of spike load was reduced. And similarly, when we have 10,000 pounds of downward clamping force, 80% of spike load was reduced. Thus, we can confirm and conclude, similarly to our analytical model, that with the presence of vertical clamping forces, spike load is significantly reduced. And to finish today's presentation, I'll provide a couple brief conclusions where I'll bring us back to our 3 driving questions that we started with. The first, how are fastener stiffness and rail seat load transfer affected by fastening system characteristics? Well, fastening system components significantly affect system stiffness, meaning that we saw that with the presence of elastic fasteners or E-clips, there was roughly a 2 to 3 times greater increase in fastener stiffness magnitude. However, these fastening system components have a minimal effect on rail seat load, only about a 5% rail seat load increase. Second is, how does fastener stiffness affect track stiffness? Well, as we saw with the preliminary analysis conducted, fastener stiffness has a minimal effect on track stiffness. And finally, how is load transfer affected by applied plate clamping force? Well, as we saw, plate clamping force has a significant nonlinear indirect relationship to spike load, meaning that as plate clamping force increases, spike load or load transferred to the spike decreases. And finally, plate uplift has a minimal effect on spike load. With the presence of uplift or vertical gap observed between the plate and tie interface, spike load is increased fairly minimally, approximately 8%. And I'd like to finish today's presentation by acknowledging our project sponsors and industry partners, and thanks to all their help, funding, and expertise. And with that, I would like to conclude today's presentation and thank you very much for your time and attention.